All right, welcome, everybody. If you're tracking along, you'll notice that the handout for this time is the same as last time, and that's because we ended up getting staggered by about a day, so it just makes sense to use this, get through this set of notes rather than keep stockpiling more and more handouts that create confusion. So we'll get through the notes today, have a reset, and then we'll be on pace for the rest of the class. No big issue in terms of timing. We'll still get to cover pretty much everything we're shooting for. Hope the midterm went smoothly. I think we should be able to return that graded shortly. I think what I would just say is if there are any questions, lingering misunderstandings as you review your graded midterm when it's returned, then just be proactive. You know, these are grad courses. The point at the end of the day isn't to pass or not to pass, or well, you should pass. The point isn't to really do anything other than build your knowledge base for your future career. And so if you feel like things that should be happening aren't happening, then let's have a conversation, you and me, or with the TAs about learning strategies, about additional resources, et cetera. We, everybody is here at Scripps because you're capable of doing the work at a high level. And if it's just not happening for any reason, then let's have a conversation about that. Okay, we've got quite a bit of ground to cover today. Maybe I'll take a minute. If there are any questions, I guess another administrative announcement that I almost skipped over is about the Wikipedia project. So that's due today. And if you have any questions, it's due at midnight, I think, is that people did. And, whereas we'll probably, in reality, all still be on our computers close to midnight. The closer you get, maybe the less responsive we'll be. So if you have questions, try to seek us out this afternoon so we can help. Smasher.
I couldn't find any examples of this on Canvas, so I don't know if I'm missing something, but is there any particular format that you want for the first draft? Is it supposed to be in any document template, or do we just kind of, send a Word?
Yeah, that's a great question. I think in the past, it's just been a Word document.
Be really brief, like from my own experience, for like all of the graphs, if you take it from the whatever written paper, crop it, it's going to be okay for this draft, but for your final draft, it's going to be all of the chemicals you made by yourself. So yeah.
So that's a great point by Wenji. If you're crunched for time now, and I'm sure many of you are because you had 2 midterms last week, for those of you doing parasitic metallics, it's fine to just do a screen grab of what you plan to eventually do in your own style. Of course, for the final version of Wikipedia, you can't have like screenshotted journal articles. That would be against the copyright. But for the draft review, that's fine. Questions? All right, let's jump in. We've got quite a bit of ground to cover around the theme of catalytic carbonylations, and this will span really a wide variety of different types of reactions. And the unifying theme is that they're going to involve CO, and they're going to involve thus 1,1 migratory insertion. And I will start with a joke that pay tribute to a former TA of the class, Tanner Jenkins, who told this setup when he guest lectured the class, and I just thought it was humorous. So I've kept it as a tip of the cap to him, so to speak, which is today's lecture. The spirit is that we will try to teach you how to build all of the commodity chemicals that you need to support modern society from the 4 real elements: wind, fire, water, and earth. Although if you're a fan like I am of Captain Planet, there's a 5th element of heart that is not shown here. And this would come in handy if you're ever stuck on a deserted island, then you'd know how to build society from scratch. But the caveat would be to do so, you're desert island would need to have been struck with a meteorite to get you all of the precious metals that you need to actually perform these reactions. Um, you might be in kind of dire straits by the time you get the chance to do the chemistry. Carbonylation reactions, as well as hydrogenations, there's something they share in common that is interesting at a high level, which is that the molecules involved themselves, H2 and CO, are largely inert to most organic reactants. And I think here is a beautiful example of where the transition metal turns on modes of reactivity that, if in the absence of catalytic activation, there's not much reactivity to speak of. And we'll see the power of catalysis across many now society supporting reactions here. So first stop is a classical reaction that you might not be that familiar with, but is highly important to society as we know it today, and that is the water-gas shift reaction. It can be thought of as a shuttling reaction where an atom of oxygen is moved between water and CO2. Why this reaction is important and run on massive scale today, largely in a heterogeneous fashion, although the examples that we'll cover will be predominantly homogeneous to be consistent with the theme of this class. These reactions are run on large scale, really for the express purpose of generating H2. And why do we need a lot of H2? Of course, that's for processes like the Haber-Bosch process that ultimately produce food that supports humanity. It's interesting, the world didn't have much of a need, humans didn't have much of a need for access to a lot of molecular hydrogen until the middle part of the 19th century. And it was only then that did the Haber-Bosch process, as well as some of the other reactions that we'll talk about today, hydroformylation, et cetera, come online. And then humans found themselves with a shortage of H2 on their hands. They were scrambling to meet the demand for H2 by reactions like taking steam and reacting it with metallic iron to make iron oxide and H2. But obviously that's a stoichiometric reaction. That's not really what you want to do. And so it was this invention of the water gas shift reaction that really lowered the barrier to access to H2 and had a transformative impact on society. In terms of operating reaction conditions, CO environment, aqueous basic conditions, the reaction is moderately exothermic. You can see how the delta G and the equilibrium constant change as a function of temperature in this chart on the bottom right of the slide. So let's look at the organometallic mechanism here. Can you get us started, Riku? We're going to take
You get like a ligand substance.
So we're going to consider a case of a tungsten catalyzed homogeneous system. Step one is you wanted to do some kind of ligand substitution. Is that what you're thinking about?
Oh, but the CO has to be
So what do we know about metal carbonyl complexes in general? So what we have here, I've tried to draw this somewhat suggestively. We've got hydroxide, which is going to be a nucleophile. I guess it's not even, why do I draw this delta minus? It's actually just minus. So we know this is a nucleophile. And then what do we know about partial charge on a metal carbonyl like this?
Yeah, probably attacks the.
Beautiful. Okay, so you're saying it attacks the bound CO. I'll try throughout the lecture to use consistent coloring just so you can see where atoms are going. If I miss one, then sorry in advance. Okay, so metal carbonyls we can think of kind of like, other types of carbonyls that we know are electrophilic. In this case, we just do a 1,2 addition. Now we've got a tungsten hydroxycarbonyl complex, and I've drawn H plus coming into the cycle. So what do you think might happen here?
Protonated.
Protonated, where would it like to be protonated? At the metal, okay? And I'm drawing this in a little bit of a lazy form of not on the oxidation state and everything. Tungsten, just quick. Now to draw this, so now you're charge neutral because you came in with the proton and you were previously anionic. And then I've drawn CO2 leaving the cycle. So what would the byproduct in that case be?
Oh, like,
What do you think?
coordinating.
Oh, what did I do? Tungsten coordinated to two hydride ligands, reductive elimination, CO comes back in to regenerate catalyst, and we're off to the races. As you can appreciate, this reaction is often, I mentioned it's moderately exothermic, often reversible, and so running the reaction conditions under, or choosing operating reaction conditions based on the chart on the bottom right to get the desired equilibrium constant, i.e. to make H2, which is typically what's desired, rather than the reverse, the retro water gas shift reaction is important. Questions on that? Okay, that's a quick primer. We'll come back to that in a later part of the lecture. So now let's talk about another classical catalytic carbonylation reaction. It's actually, as we speak here in the year 2025, it's a collection of related reactions. The first of its kind is known as the Monsanto acetic acid process. And from a 40,000 foot view, what it does is it allows conversion of methanol, which there are a lot of ways to get your hands on methanol. There's you can source it from biorenewables, you can do syngas, you can source it from syngas. It's a way to upgrade methanol through the atom economic insertion of CO into acetic acid, which I think we have appreciate. I mean, I used a bunch of vinegar to do cleaning of my pots and pans last night. So we all have an appreciation for why acetic acid is useful in modern society. And of course, is a very useful building block for various esters. And the Monsanto acetic acid process and its related siblings are responsible for 80% of 7 billion pounds of acetic acid production. Initially discovered in a cobalt catalyzed variant by BASF in the 1960s. And you can see the reaction conditions are quite forcing, or were quite forcing. And so this motivated a pivot to precious metal based approaches, rhodium in the case of Monsanto, and iridium, as we'll see in the case of the Cativa process. So an interesting case, and there's actually several cases like this in this particular lecture, and also in the history of organometallic catalysis, where a process was initially discovered with a base metal, and then there was a pivot made to the precious metal version because the reactions are more tractable, more easily understood, have better operating conditions. And now in the 2020s, there's motivation to go back and see if you can redevelop some of these reactions with base metals, because the price of the corresponding metals has continued to increase, and there's been geographic instabilities that motivate or that complicate sustainable sourcing. Okay, so the catalyst that we're going to use for this Monsanto acetic acid process is the one shown here. Rhodium dicarbonyl with two iodide ligands. And this is the active form of the catalyst. You can use many different rhodium salt precursors, and they all will get you here to the active form of catalyst. Let's warm up our brains with a quick electron counting exercise, although many of you, I'm sure, are sick of electron counting from the midterm, since there was plenty of it on that, but let's do a quick electron count. Catherine, what do you got here? First oxidation state of rhodium. Rhodium +1. Rhodium 0 is D9, so what does that leave us for rhodium +1? D8. 2 X-type ligands, 2 L-type ligands for a total for how many electrons? 8 electrons from the metal, 16 electrons. Overall electron count, D8, square planar. And we note at the outset that it's anionic. So what are we expecting it to do? We're expecting it to be nucleophilic, electron rich, and engage in that type of chemistry. All right, let's get us started here on our cycle. It's actually a dual cycle. So that's the first thing to notice. We've got catalytic iodide in the form of HI, catalytic rhodium. So step 1, HI plus methanol yields what? EI? Oh, somebody shouted already. Who said? Riku? Sebastian?
Thank you. I think it was Sebastian.
Sebastian.
Oh,
Now you're on the hook for it.
That's fine.
All right. Sebastian. Methyl iodide, you said. Good. All right. Now I've drawn this coming in to react with our rhodium salt. So what do we expect might happen here? Okay. Oxidative addition. We were doing oxidation state assignment. Now, rhodium 1, and we're at rhodium 3, we've just done oxidative addition. And then our electron count here is what, Sebastian? 14 start. All right, we've done 16 to start. Doing that. This is still all right, CO is going to come in now. You can see that from how I've done this. But what elementary step do we have next? We've got an 18 electron metal center. So we've either got to do something intramolecularly or unimolecularly, or we've got to do lose a ligand. So what do you like to have happened here, Sebastian?
Like one migration, and then the CO comes in and replaces the methyl that would have.
Okay, you said 1, 2, but I think you meant 1, 1, 1, 1 maybe. 1, 1 migratory insertion into CO from the methyl. And then what is the role of this second equivalent, or I guess it's technically the third equivalent of CO here?
Prevent the reaction from going backwards.
Ah, beautiful. So if we didn't have this, we'd have an open coordination site, and then we'd have this problem with the reaction being reversible and non-productive. So we trap with CO. We've now gone from, in so doing, we've gone from 18 electron complex to 18 electron complex. And we're almost there. So you may as well get us home here, Sebastian.
So then does your water add in and displace? Oh, no, wait. Actually, yeah, wouldn't you do that and then you reductively eliminate HI after?
Yeah, 2 possibilities, and both could be reasonable. One would be to look at that rhodium acyl and say, that looks kind of like acyl chloride or or something like that, and just hydrolyze directly in an outer sphere process. And then the other would be, so that's one limiting scenario. And the other limiting scenario is I think more what's commonly invoked here, which would be what, Sebastian? So what I think what you proposed is not unreasonable. So that's a fine answer. Like, what would be one alternative mechanism to the one that you proposed?
Yeah, displacement or removal of one of the iodides. I guess that would dissociate and then water can add in and then do that next step.
Yeah, so I think we just call this maybe, oops.
Oh.
So just reductive elimination of the, and probably this too is, I don't have this drawn, but you can imagine this also potentially being reversible because you're making a strong electrophile and you're making a metal catalyst that's nucleophilic, but there's a fast hydrolysis process happening on the back end, so driving the reaction forward. It's a CI reductive elimination to make the acyl iodide. And then hydrolysis regenerates the catalytic HI. So then high level, what is the role of this second cycle? Why not just use methanol directly? Then you would do oxidative addition to the methyl oxygen bond and then push arrows and get to the product without any of the trouble of the HI. Yeah.
Methanol without HI, you mean? Without HI
Yes.
cycle? Because you cannot oxidate add to methyl oxygen. It's not that nearby.
So you have a real kinetic problem on your hands. And I think if you just in classical organic chemistry terms, I would just describe this as an Oompa strategy where methanol, you have this issue where in general, like the methyl oxygen bond is going to be, there's going to be a kinetically high barrier to add into it. Also, methanol plus base plus a metal catalyst is normally going to lead to the methoxy adduct because the delta minus character is on oxygen. So it's a nucleophile effectively. So you pull it with catalytic HI to make it an electrophile. And then that's the secret sauce here. And I realized I've drawn this metal iodide, but I meant methyl iodide. Okay, questions on this? Ning-Shi.
The reductive elimination of acetyl iodide looks kind of unfavorable. Is it just driven forward by hydrolysis?
Why does it look unfavorable to you?
I mean, you would think that if you have acyl iodide, it's unstable, and if you have any metal species, it's gonna do oxidative addition, right?
Yeah, well, I think you're there are two different concepts in your answer. So one is that one is like the stability of what the stability / reactivity of what you're making. So you're saying what you're making is very kinetically reactive. That doesn't mean that the barrier to make it is intrinsically high, if that makes sense. So I think it's that, and that's why I added this arrow implying reversibility followed by hydrolysis. You don't see, I mean, and then we'll talk about this in the rate law, you don't see these steps. And so, and I can talk about other mechanistic facets of this chemistry and the and then, you know, if you're interested, we can take a deeper dive offline into the mechanistic evidence for direct hydrolysis, as Sebastian proposed originally, or his second proposal of CI reductive elimination. Okay, let's take a peek at the rate law here. So in general, when you have a dual catalytic cycle, and you think about the concentrations of the reactive species involved, a good place to start for thinking about what the turnover limiting step would be is the part where the cycles cross, because those are going to be the least, the species that exist in the lowest concentration in general. There would, I'm sure you can find exceptions to this, but in general, that's a good place to start. So here's our rate law. We've got positive order in iodide, which here the iodide rests as the methyl iodide. And positive order in rhodium. So yeah, what do you like here for a turnover limiting step?
I think oxidative addition.
Yeah. Good, and the rate law is independent of CO concentration, which is somewhat uncommon in catalytic carbonylations, as we'll see in other examples. And operationally, empirically, it has been found that this reaction often work best with a substantial amount of water added. So we see this role of water in the hydrolysis step. Then we'll talk about secondary roles that it can play in a moment. Okay, a little bit more nuance into the mechanism. So first we'll talk about some off-cycle species, and then we'll talk about the mechanism of the oxidative addition step in particular, which some of you I'm sure already have a good hypothesis for what might be going on there. So let me draw your attention to this key step here. I've just repeated stuff I've drawn before. Some of these steps can be studied stoichiometrically through mechanistic organometallic studies. So here's, let's zoom in here. Oxidative addition of methyl iodide gives the corresponding triiodide anionic complex. Then we've got the 1,2 migratory insertion. We have the open coordination site. What we want to happen on cycle is trapping with CO, as Sebastian mentioned to us. But if trapping is insufficient, and this can happen if the CO pressure is insufficient, then what do we know about metal halides with open coordination sites? They like to form bridging interactions, and that indeed can happen here. So if CO concentration is insufficient, CO pressure is insufficient, you will form this mu2 bridging iodide complex, which has been characterized by X-ray crystallography. And this species can then struggle to find its way back on cycle. So this can be a deactivation mechanism. We'll talk about other deactivation mechanisms in a moment. And then what we hope to happen is, of course, capture with CO prior to reductive elimination. Let's focus a little bit more on this now oxidative addition step. I'll provide here the data point that the anionic species is very highly reactive. If we just zoom in on the oxidative addition step, specifically, the anionic species drawn is 5 orders of magnitude faster than a representative neutral form. So here what we've done is removed one CO ligand, replaced it with a triphenylarsenine ligand, added a second triphenylarsenine ligand. So it's overall charge neutral. The triphenylarsenines you can just think of as triphenylphosphines. They're isolobal, they're highly sigma donating. So from a ligand perspective, you've really pumped in a lot of sigma donating character here, and yet the anionic form is still much more kinetically reactive. Does anybody want to rationalize that? What do you think there, Mike?
It's more like a nucleophilic attack by the rhodium center rather than like so more like an SN2 than a
Okay.
insertion.
So Mike's proposing SN2 type oxidative addition here to rationalize this observation. And maybe I'll stick with you, Mike, if you wanted to, so what are the other, thinking back to our oxidative addition lectures, the other main categories would be a classical inner sphere concerted process or a radical process. So if you wanted to run some experiments to potentially rule out those other possibilities, what might you do?
So if I wanted to rule out classical, I'd try both a more electron poor species, because if it was just the 2 electron concerted oxidative addition, that should go faster with more electron poor halides, right?
What halides do you have in mind?
So we could take methyl iodide and then add a cyano group.
Oh, I see.
It would be stable, or, I mean, I'd assume still with an SN2 type, that would still go faster. So I guess you'd more so want, like, I think it's easier to rule out the 1 electrons.
Okay, let's do some of those first.
Yeah.
Okay, so let's talk about radical. So you have, it sounds like you have some ideas of radical. So what are you thinking about there?
So isn't that, if it's just single electron transfer from rhodium, then you need to choose 2 halides that have like same steric profiles, but they have a different E naught CV.
Okay, beautiful. So I think one of the classical ones would be to try methyl tosylate,
Yeah.
which would be good in an SN2 pathway versus methyl iodide. But bad in a radical pathway, so that's totally reasonable. Anything else on your mind for that?
I mean, other than that, you try having a radical trap on your substrate.
Okay, radical trap or radical flock?
What was the second one you asked?
Radical trap or radical clock?
Clock also works. Yeah, I mean, you want it to react faster with whatever's else is on the
So
molecule.
here's one. This would generate the cyclopropyl-methyl radical in a radical process, which has a very fast 10 to the, what is the first order rate constant, 10 to the 8, I think, or something like that. Good, okay, and then the classical, anybody have any thoughts on classical concerted? Maybe I'll call it concerted rather than classical. Open it up, if anybody have thoughts on this.
Would you change the halides you're using and see where the halides are? Like if trans were the answer.
Oh, okay, like that idea, the stereochem. The one way I think that Amy's thinking here is to try iodide versus bromide or potentially tosylate and see if they go cis versus trans. Have to make some assumptions that doesn't break other parts of the mechanism, but that's reasonable. You could think about using isotopically labeled iodide, but then you need to be confident in 2 things. One, that you're not going to face secondary processes that undermine your ability to interpret the data. And second, that you can have analytical techniques to interpret the data in general. Al?
If oxidative addition is your turnover limiting step, I feel like you should observe a solvent effect which should stabilize your transition state. And consequently, that transition state should have a noticeable electronic effect, which you can observe through a Hammett plot.
Okay, oh, you packed in a bunch of stuff there. So the first was solvent polarity, solvent dielectric constant. More polar solvent should favor SN2 pathway because you make charged intermediates. And then you also said Hammett, which I think ties into Mike's point about making some electronically modified electrophiles. Good, okay. Sebastian, do you have a question or an itch?
Would you be able to disprove the SN2 type oxidative additions or, pass some down onto them by just using something like tert-butyl iodide or neopentyl iodide and just show that the other oxidative addition pathways would probably still work? Is that something that people do?
Yeah. Indeed. So the extreme there is to go T-butyl, that'll work in a radical, gonna work less well in a concerted or SN2 type pathway. Yeah.
Do you ever see SN2 type with like SP2 or SP like halides?
Generally, those have to go the concerted pathway, just an analogy to classical E-block chemistry.
Yeah, so could you just try with an aryl iodide here, see if you get this phenylacetic acid or phenylacetate?
Great, okay. Love the thoughts here. Anything else? Okay, so this is the just restating the conclusion that we have come to. And I just want to draw attention that if you, and this is a point that Amy raised, if you were somehow able to differentiate the halide here, and we talked about ways to do that through isotope labeling or through using a different halide, you would get those trans, and that would be an indicator. Okay, now let's talk about some other side reactions, deactivation pathways, where things can go wrong. And we talked about the fragility of this E intermediate. What we hope happens on cycle is it gets trapped by CO, but other things can happen. Dimerization is one. But you also have this precarious situation where you have HI in your reaction, and you have also an organometallic intermediate. And so that can be a recipe for proto-demethylation, redox neutral at the metal center. And that can create problems for you because what you've done here is you've now created a species that is found nowhere on the catalytic cycle, rhodium-3 triiodide with some number of CO ligands bound. And then what that can do is, like we talked about, aggregate actually irreversibly into insoluble junk, polyhalide bridged species, and that can be a perverse deactivation mechanism that then is autocatalytic. But there's a silver lining, which is that there is a rescue pathway that is built in, and it goes back to that point I made before about the reaction empirically being found to run best with 10 to 15 mole volume percent water. And so what happens if we get to this triiodide, this carbonyl complex in the presence of water? Any thoughts? Yeah, come on.
I think first replacement with the iodide and going forward to rhodium oxide complex, rhodium oxide specifications, or adding to the carbonyl.
Okay, let's unpack that. Adding water or base to the carbonyl. And how would that connect to something we covered earlier? in
It's like
class?
a gas water shift.
Beautiful. So you can, and I won't draw all the steps here, but you can water gas shift your way back to the active form of the catalyst. Now, in this case, you're not generating, or you hope to not be generating H2. Those reducing equivalents are going to reduce the rhodium-3 back to its catalytically active rhodium-1 form, where the byproducts are CO2 and HI. So, while widely used, this reaction is not without its disadvantages. One is that we rely on H2 for the hydrolysis step, for the water gas shift, but then the product from this reaction is acetic acid. And so you then have this issue with your distillation that you need to remove H2, or you need to remove H2O water from the product stream and set up a complicated fractional distillation to do so. And then we're also losing some of the CO. Not a perfectly atom economic process as advertised. We're losing some of the CO to CO2 through this water gas shift. And then you have this other problem where you're using HI, but of course that's growth to your reaction vessels. So these issues and ultimately compromise catalytic turnover. Remember that this is the commodity chemicals space. So it's not sufficient, like if you're working in pharma and you run a Suzuki reaction and you have 0.1 mole % catalyst loading, or even sometimes 1 mole % catalyst loading of palladium, that's a fit for purpose solution because the value of your product is so high. In this case, you're making vinegar. The value of your product is super low. So everything where you can save money or create efficiencies, improve catalyst lifetime, understand deactivation pathways helps you. And so some of the suboptimal aspects of the Monsanto acetic acid process have motivated development and extensive research into alternative processes. I'll cover them briefly, but I won't go into as much depth here, just in the interest of time, because they share a lot of the same mechanistic features. One idea that you might have if you had been following the logic of this part of the talk so far, part of the lecture so far, is water creates all these issues. So what if we just ran a process that was water-free and we didn't target acetic acid, but we instead targeted acetic anhydride? And that idea is certainly has merits, and others have thought that before, and that led to the development of the Eastman acetic anhydride process, which is very similar to the Monsanto acetic acid process, but rather than water for this key acyl iodide addition step, it's the deprotonated form of acetic acid, lithium acetate, is used so that acetic anhydride is formed directly. And then the advantage here is that your product is also a desiccant. So if you encounter trace water, if the reaction unproductively turns over and generates some water, you have a means of scavenging it. And then in the presence of base, any acetic acid that you generate from hydrolysis of the acetic anhydride can re-participate as a nucleophile. What we'll spend a little bit more time talking about is the BP's version of the Monsanto acetic acid process, which is called the Cativa process, where they wanted to get even more expensive on the metal side. Well, that's not really the motivation. They wanted to have a even more efficient catalytic process and were willing to take a hit on the metal cost. And so went to the third row, focused on iridium. Kinetics are a little bit different, mechanism a little bit more complex here. We're just going to focus on, from an organometallic organometallic perspective, some of the key elementary steps. So let's zoom in on that key oxidative addition step, thinking about what differences we might anticipate between iridium and rhodium. Switching to iridium here gives you 150 times faster oxidative addition. What are the reasons for that? We talked about, it goes back to themes from periodic trends. You're forming a stronger ruthenium metal carbon bond by being in the third row. And so that ends up getting reflected in the transition state energy. And then in general, the farther down on the periodic table you go, the more those elements can support higher oxidation states. And because you're getting to a metal +3 oxidation state here, that's favored as you go into the third row of the transition metal series. But I think you can anticipate that this is going to create a problem. So you get acceleration in your oxidative addition, but now you've created a stronger bond that you need to break in your migratory insertion. And what did we learn about in migratory insertion lecture? If you think back to that, what are the periodic trends as you go down a group in migratory insertion? Madi said, as you go down, you will get slower. So we would expect iridium to be faster. And that's predominantly, if you think back to those lecture notes, a ground state stabilization phenomenon. So you have a more stable ground state with iridium. The transition state geometry is largely conserved. And so you have a higher transition state decline. So you've helped yourself in one step, but you've made life more challenging in the second step. So empirically, this was found to be surmountable through a key promoter, which is this ruthenium tetracarbonyl biiodide. So what does this do? What are some strategies we learned for promoting 1,1 migratory insertion in cases where it's challenging?
Increasing steric hindrance.
You can increase steric hindrance, but that we don't have any ligands. We don't have any really tunable ligands on the metal. So that's not a great option here. And a trapping ligand, that is true, but the trapping ligand we want in both cases is going to be CO. Alex.
Using a Lewis acid. CO.
Okay. Lewis acid, or in general, so there's a couple related concepts here. Lewis acid activation, and then there's making the metal more electron poor, making it cationic, increasing its oxidation state. So what is this ruthenium scavenger doing here? It is, what is this ruthenium additive doing? It turns out that it is scavenging an iodide to go from anionic to now charge neutral. And that has effectively the same effect as if you go from charge neutral to cationic, you're increasing the oxidation state. Sorry, you're increasing the overall charge, making the metal more electrophilic, more electron poor. Sorry, I'm got marbles in my mouth today. So that will sequester iodide, open that coordination site, make intermediate charge neutral. And that gives us 700 fold rate acceleration in the charge neutral versus anionic form. So from a metal bond strength perspective, we're accelerating oxidative addition. We have an additive now that can rescue what would be a challenging 1-1 migratory insertion, and that's the key recipe for that BP Katiba. Yes.
Why does it not do that like at any in the process? Like, wouldn't that make your oxidative addition?
Yeah, good question. These, I think, as I've tried to represent it, this will all be reversible. And so I think you could expect it potentially to coordinate, it might decrease your effective concentration of your free oxidative addition complex. But I mentioned the rate law in this process is different. And so that term, unlike in the previous case, that term I think is not in the rate law. So decreasing that concentration doesn't decrease the overall rate. Yeah, great question. Okay, we'll shift gears here and now talk about olefin additions. The classical one here is hydroformylation, and then we'll talk about some modern variants of different olefin addition processes. Mechanistically, we will focus most of the attention on the oldest version of this, which is the cobalt catalyzed version. The most widely used now is the rhodium catalyzed version. And so I won't just like rehash all the mechanistic stuff. We'll present that in the cobalt, and then you can think about what the similarities and differences are going to be in the rhodium case. So this hydroformylation process reaction discovered by Otto Roland, industrial chemist working at Ruhr. And it was discovered serendipitously by looking at the effect of alkene additives in the Fischer-Tropsch reaction. It was commercialized and then branded by the marketing team at Ruhr as the OXO process. And I found these statistics interesting that hydroformylation is used to produce north of 14 billion pounds of terminal aldehydes per year, which works out to about 2 pounds per year per person, which seems kind of like a lot that we're consuming 2 pounds of linear aldehydes a year. But I think if you step back and think about all of the ways where linear aldehydes are used, for example, reduced to alcohols and used in detergents and so on and so forth, maybe it's not that surprising. There's a really interesting review here, historical account that I would just draw your attention to, and this will be available as one of the readings for today because it's a historical perspective. Also talks a lot about Otto Roland's life and career and has some interesting vignettes like copies of his transcripts from various points in his education and things like comments from his supervisors like he's a good hard worker. So that's something to be conscientious of. If you ever make it big, then your Scripps records might become part of the public domain at some point. Okay, let's talk about mechanism. We're going to start with a familiar looking complex, or one that's hopefully familiar at this point in the lecture. Cobalt 2 CO8, cobalt carbonyl. And the key step to get into the cycle, two key steps that are going to be going into the cycle. One is this bimolecular oxidative addition of H2 across the cobalt-cobalt bond to make cobalt hydride, which is, we've talked about properties of metal hydride. This is one that's acidic and has a weak metal hydrogen bond. So that's the first step. And then the second step, we can do a quick electron count of this. So we orient ourselves. So anybody want to help me with this? Cobalt, hydridocobalt, tetracarbonyl. Yeah, what do you think?
It's a cobalt one, so it's
Cobalt plus
D8
one,
electrons.
D8,
5 ligand, so it's 18.
18 electrons total. Okay, so that is our first clue that that's not going to be the reactive form. So it's going to need to lose CO, open a coordination site. You know, in principle, you can lose the trans CO or this, the axial CO or the equatorial CO. And I'm just drawing the equatorial one because that's the one that allow us to do productive downstream chemistry. Okay, give us a little bit more here, Yao. So we're going to have some familiar looking steps: olefin coordination, hydrometallation. Olefin coordination, hydrometallation, trapping with CO. And that can happen with two regiochemical orientations to potentially give rise to the branched product, so-called branch product shown on the right, or the linear product, which is the one we're going to form through the remaining steps. And already you can get a sense of what steps could potentially be involved in regio selectivity determination. Could it be the hydrometallation? Could it be the CO trapping? Could it be the migratory insertion? Could it be the downstream H2 oxidative addition reductive elimination sequence? And we'll come back to this point, but that's just something to keep in the back of your mind. Okay, so yeah, we've got this intermediate. Give us another step here.
So 1-1 migratory insertion.
1-1 migratory insertion. So that's going to create for us an open coordination site here. Okay, so let's stay on cycle here. And then what's going to come in at this point, Yao?
Show me the condition again.
We've used some CO, we've used some metal, we've used some olefin. There's one component we haven't used yet. Hydrogen, okay. Sorry if you said that, I just didn't hear you. H2 comes in. We've got that tempting looking open coordination site that H2 is happy to coordinate to. It will form a sigma complex initially, not drawn here. Form dihydride, reductive elimination, then we'll form our product. Okay, and then we've got something off cycle going on here. So what do we think could happen here? And I'll give you a hint, is that we need to, it empirically is found that these reactions, you know, like if I asked you all, how many of you have run hydroformylations in the lab? Probably nobody would raise their hand. One of the reasons is that while these are, the operating conditions are not that user-friendly for most practicing organic chemists because they typically require very high CO pressures. Some of the more modern ones not so much. We'll see some encounter some counterexamples of that, but for this manifestation, early manifestation, these are ultra high pressure CO.
I think it's another CO coordinate.
So you've got a ton of CO, you've got an open coordination site, and so you're fighting this battle of CO coordination. You fight the battle to get on cycle in the first place. You fight the battle to stay on cycle. But a lot of times, these battles that you fight have the side benefit of often providing robustness to the catalytic cycle because they prevent deactivation, like we saw forming bridging aggregates and so on and so forth. Interesting DFT study I would draw your attention to if you want to see more about the potential energy surface for this and the relatively complex rate law. All I want to say about the rate law is that this is, there are multiple partial order components and negative order in CO because of the need to dissociate CO to get on cycle in the first place and the potential for CO to capture on cycle intermediates and sequester them off cycle. Common byproduct, and we already, I think Eugene asked a question anticipating this in the hydrogenation lecture. Common byproduct is hydrogenation, and that's another reason why the reactions in practice often need to be run with high pressure of CO. The cobalt system was a little bit of a fixer-upper when it came online. In the mid-1900s, when this was discovered and developed, the product that was most desired was the linear product because that could be reduced to the corresponding alcohols or amines that were then used in detergents, lubricants, etc. But this process only offered about 4-to-1 linear to branched ratio, and we'll come back to that in a moment. The mechanism was elucidated in the 1960s by Heck and Breslow. It's the Heck that you're probably thinking of, Richard, but not the Breslow that you're probably thinking of. It's a different Breslow, David, not Ronald. So working together at Hercules Chemical, they elucidated the mechanism, and this is most of the findings from this 1960s papers are still the ones that people point to today. Shell made an important contribution that is also important within the broader themes of this class. They were unsatisfied with this linear to branch ratio of 4-to-1 and found that it could improve to about 8-to-1 through addition of phosphine additives. And so the types of phosphine ligands that work here are typically the trialkyl flavors, and one that's effective is tri-T-butyl phosphine. Tri-N-butyl phosphine also works well. There's an interesting little subtlety here that typically these, if you think about the scale that these reactions are done on, then the preferred method of purification is not some type of chromatography, but rather distillation. And so using many trialkyl phosphines, a problem that arises with distillation as a means of purification is that those phosphines are volatile and will actually be kicked into the product stream. And so Shell also was clever enough to develop non-volatile phosphines that perform similarly in terms of the catalysis, but have much lower boiling points like the one shown here. So the phosphine additive trick by Shell solved some problems, or solved some issues, but didn't solve all of them and introduced some new ones. So what are the consequences of phosphine addition? One is that phosphine ligand addition. So one is that when you have phosphine ligated metal centers, now the bond, as we covered earlier in class, now the bond strength to the corresponding carbonyl ligands goes up. Why is that problematic? Because we just covered that you need to lose the CO to get on cycle. So you could anticipate, and indeed you observe, that there's a suppression in the rate. So these two features go hand in hand. we were able to reduce the CO pressure operationally, which was good, and increase linear branch ratio, but then now the hydrogenation is more of a problem. And again, these two go hand in hand. And they also started observing another type of byproduct, which initially they thought was a bug, but then they realized, because they're clever industrial chemists, could be developed into a feature, which is that the aldehydes that were generated would undergo in situ reduction with H2. And that was, they recognized that was an opportunity because the alcohols were often what were desired by end users. And so they developed a process by which they could take the product stream from a process called SHOP, Shell Higher Olefin process, which we'll cover briefly in the metathesis lecture. So it's a form of metathesis that gives you mixtures of olefins. Then through a combination of chain walking, hydroformylation, and in situ reduction of the aldehyde, they could get to these valuable primary alcohol products and relatively good linear to branch ratio.
Sir, can I ask a question?
Mhm.
I understand about the point, but I kind of still don't see, like, look at the catalytic cycle, why adding bulky phosphanes for the ligand.
Okay, let's come back to this in a moment, because we're going to talk about ligand design in the context of rhodium. And if that does not answer your questions, then please remind me to. So eventually, as we saw in the case of the Monsanto acetic acid process, initial discovery with cobalt displaced by rhodium. Same story here, initial discovery with cobalt, and then eventually Union Carbide and industrial chemist Pruitt took this on and developed a rhodium-based system that had a lot of advantages: low pressure, faster rates, and then the ability to engage phosphine ligands to tune linear to branched selectivity. So one of the key findings early on was that addition of a triphenylphosphine as a ligand improved linear to branched ratio. What actually happens in the flask? It is complex. So it's basically every combination that you can imagine of CO, a hydridorhodium, and then some number of COs, some number of phosphine ligands. These are all formed. And through some painstaking experiments, it was eventually found that as you go right and have more CO ligands, you get to higher activity. And as you go left and have more phosphine ligate, and this gets to Riku's question, you get higher linear to branched selectivity. And the magic ratio is the one highlighted here in yellow, with 2 phosphines and 1 CO about the rhodium center. Why is that important? Because that maps in nicely to a bidentate ligand design that we will talk about in a moment. Okay, so let's zero in on in solution here. Now we're not looking at the yellow highlighted form. We're looking at this one here for anybody who's keeping track. So 5-coordinate rhodium. And you can monitor, this is a stable resting state, so you can monitor speciation and assign the stereochemistry here with quite high fidelity. So this species exists in an 85 to 15 equilibrium, with the favored form being the so-called equatorial form with 2 phosphines around the equator of the metal. And that's favored compared to the equatorial axial form with 1 phosphine at the equator and 1 at the axis. The preferred geometry for high selectivity is, sorry, it's completely backwards. This is is the one shown here. And so this informs ligand design. Okay, let's kick this out now to problem of the day number 1 from the handout where we can dig into this a little bit more in a little bit more depth. So we've got a collection of Xanthos derived ligands. And I'll give you a chance to think about that and just apply what we just covered. And I think this one, just in the interest of time, we'll kind of do on the fly together. So we've got systematically increasing bite angle, and we talked about how increased bite angle is going to favor this equatorial form that is more selective. We'll get some of the ratios down here. We see as we go increasing bite angle, we get higher linear selectivity. And start to get to really high, more than 50-to-1 selectivity in the best case. But there's something interesting here, and I'll put this data up and then we will linger on this for a moment. Okay, so it looks like we have a correlation here between bite angle, natural bite angle, and linear to branched ratio. And then let's look at the experimentally read out EE to EA ratio. Do we see a correlation there? Riku's saying no. So you'd have to be, maybe you could argue between L1 and L4 and L3 if you didn't include L2. But there's certainly, at best, a very weak correlation. Okay, so if we agree on that, then I would ask the question of why. Yeah, Marty.
The more the bite angle, the more steric hindrance on the metal. So it favors metal to bend in C1 instead of C2, because C2 makes it a branched alkyl ligand, so it makes it more sterically hindered. So you'll be in equilibrium between one migration to C1 or one on C2. It favors C1, so they get more linear.
Okay, I think that's a beautiful explanation for why. And so this gets to a question of what is actually, first question to consider is what is the selectivity determining step? And this has been something that's been studied, and now in contrast to what we covered with cobalt, you're in the second row, so you're forming a stronger rhodium carbon bond upon hydrometallation. And so I think the general prevailing belief is that the hydrometallation is selectivity determining here. So here's what Adi was saying of this transition state. And as this gets wider, it gets more encumbered and favors linear. Is that a fair reflection of what you said? Okay, and now, so I think that's a nice explanation here, but what about this EE to EA ratio? Why is this not seemingly reflecting what we see in the linear to branched ratio? Al, any thoughts?
Maybe the EE to EA ratio is not just affected by sterics, but also the electronics of the phosphine, if they're sufficiently different.
Okay, there could be an electronic component, but they're all triaryl phosphines. So I would say electronically, probably similar. Yeah, Julian.
Is it possible that the EA form does not do the migratory, does not do the migratory insertion, but only the
So even if the ratio of the EE is lower, it's the only active form that is able to perform that elementary step.
I think you're hitting on the key point here, which is that the linear to branched ratio is reading out kinetics. It's the delta delta G double dagger between the linear to branched hydrometallation transition states. The EA ratio is reading out thermodynamic, the relative stabilities. And we talked about, in fact, you had a midterm question on the concept of Curtin Hammett, where the thermodynamics of the intermediates and their stabilities is not necessarily a predictor of the kinetics and ultimate product selectivity. So in terms of ligand design, I think we're doing okay on time here. So ligand design, folks have played with this this concept and really gone to extremes. One of the most effective extreme wide bite angle ligands is the one shown here, Bisbee, and you can see how this wide bite angle can get extremely high levels of linear to branched selectivity. Won't say too much about relative reactivity other than to say that the reaction is sterically sensitive, as you might expect if the from the steps that are involved, the olefin has to coordinate, it has to undergo a hydrometallation. Both of those steps are going to the barriers for those steps are going to be sensitive to sterics. Some applications here, hydroformylation, we talked about its applications in terms of making surfactants, detergents, also a high number of applications in fragrances. We think we all appreciate that aldehydes have unique smells. And so, and I think in Otto Roland's early work, as well as it's a common story that we'll see also in the Wacker oxidation, that the smell out of the reactor of the reaction, the product stream immediately indicated the presence of aldehydes. And so these olefin-derived aldehydes have value as fragrances, and even minor levels of enantiomer enrichment can really change the olfaction sensation, the olfactory properties. Hydroformylation has played less of a role in pharma, and that's because in general, the inputs for hydroformylation are alpha olefins and the outputs are linear conformationally flexible products, which is typically not a good recipe for drug compounds, but there are some interesting examples, and one is shown here, synthesis of vitamin A acetate, where in a retrosynthetic sense, this central olefin of the tetraene is disconnected via Wittig or HWE reaction to the primary or to the alkenyl, the enal shown here, which then can be backtracked to an alkenyl diacetate complex starting material. And you can imagine how a branched selective hydroformylation here is a nice entry into this key building block. But far and away, the biggest applications are in the commodity chemicals space. Okay, problem of the day 2. Hopefully this will be one that is somewhat fun for this audience with many students from total synthesis groups. We're going to do a retro of the molecule shown here, DEHP, a plasticizer. But we have some constraints that we need to make everything from true feedstock, so C3 or aromatic. And a good hint is that you're probably going to want to use at least one hydroformylation, given the where this is appearing in the lecture. So take a minute to sketch out some ideas. I think everybody is going to do the same first retrosynthetic disconnection. So I just took the liberty of drawing that up, which is this. Probably going to want to start from this primary alcohol and from this anhydride. All right, Marty, you've got a initial disconnection that you like here.
I wanted to make this compound via exhaustive hydrogenation of an alkyl product between butanol, which can come from propene and hydroformylation.
Okay, I got it. Butene.
Butanol.
Okay, yeah, I got it. Okay, all right. So I think so you're gonna start with propene, C3. You're gonna do hydroformylation. Here's that disconnection. Now you have butanol that you're going to, you said aldol, I think. I heard aldol. Stereochemistry here is not important. And then exhaustive hydrogenation to pretty direct, pretty good. What about the top fragment here? Let's take this one step further.
That one?
The phthalic anhydride, yeah.
I can't use palladium, right?
Probably not for the scale that this is made on. Pierre has a thought.
Just take the orthoxylene, xylene and then oxidize like crazy and then dehydrate.
Okay. One orthoxylene. Then you want to do exhaustive oxidation and then dehydration, right? Okay, anything else? Any other thoughts? Not that many bonds to disconnect. There are some others. Another one you could think about would be benzoic acid, which you're going to get from toluene, metallate, quench with CO2. And then probably the last, maybe not, maybe there are more, I don't know. One that is actually done on large scale is this naphthalene opening where you're with the vanadium oxide catalyst getting to the same. Okay, good. Questions on that? So we put a heavy emphasis on the importance of linear selectivity, and that was true for much of this 50s, 60s, 70s. But you will recognize that if you instead favor the branched, then there's an opportunity for an anti-selectivity control, and that's been a big motivator through the 80s, 90s, and into the 2000s. I won't say too much about it, other than to say, to just give a snapshot of some ligand classes that folks have had success with. And there's the binap-phos structure from Nozaki and Takaya, and Clark Landis from UW-Madison developed this diaza-phosphorylane ligand architecture. And the only point I want you to take away from this is that the ligands that work best here are not necessarily the same ligands that you see in hydrogenation or in atrope selective cross couplings or in other types of reactions because of the need for simultaneous levels of control of regioselectivity and an antioselectivity. So in this case, to favor, to just linger on that for a moment, to favor branch selectivity, you're going to want narrower bite angles, but then you want to build in stereochemical information. And so those are some of the design principles there. There's a closely related process that I will say almost nothing about, which is called hydroaminomethylation. And effectively all it is that you do a hydroformylation in the presence of an amine. That amine can condense with the aldehyde that you generate in situ to make either an imine or an imine slash either an imine or an enamine slash aminium that under the reaction conditions with H2 present can further be reduced to give the corresponding alkyl amine product. First developed, it was appreciated very early on that this could be done, developed by Walter Reppe at BASF, already back to the cobalt days. So I think mechanistically, there's not too much new here, so I just won't say much about it other than to introduce you to the fact that that can be done. What I will linger on for a moment, and then we'll, I think, maybe just take an extra couple minutes to talk about the problem of the day, is this process, which is at first glance looks similar to a hydroformylation, but you'll notice that the carbonyl is in a different oxidation state in the product. So this is called, in the literature, most normally referred to as alkoxy carbonylation, or if you instead make an amide, it's called aminocarbonylation. I personally, that name doesn't make any sense to me. I think it should be called hydroxy alkoxy carbonylation or hydroalkoxy carbonylation, but maybe people don't like to say that, so they just call it alkoxy carbonylation. I think it's very confusing, but nobody cares. This is what people in the literature use. So you can think of it like a hydrocarboxylation is maybe more. And the key point is that now you introduce the carbonyl at the carboxylic acid oxidation state. So if you need that in your final product, you don't need to resort to pinic oxidation of your aldehyde product or something else. So the cartoon version of the mechanism is shown here, simplified mechanism. Low valent metal, so one of the common ones here is palladium. Palladium plus a mineral acid will generate palladium hydride, so oxidative addition, palladium 0 to palladium 2, hydrometallation, CO association, and then migratory insertion to make an acyl palladium. As we've talked about, that acyl palladium you could view in a couple different ways. You could view it like a acyl halide surrogate, or quasi-acyl halide, where you're going to get an outer sphere alcoholysis or an inner sphere alkoxy ligand coordination followed by reductive elimination. And depending on the details, the metal, the ligand, the incoming alcohol, either of those mechanistic extremes can be operative. So that's the overall recipe. And then problem of the day number 3, and also goes hand in hand with chemist of the day. Does anybody recognize? No takers? Alexanian from UNC. Is it Eric with a K or a C? The K? You double check. I always get confused. So he trained with Hoveda, Sorensen, and John Hartwig, and has done a lot of nice carbonylation, metal catalyzed carbonylation chemistry, radical chemistry, So some in the audience may be more familiar with his HAT type chemistry. What did we, with a K, okay, I get this confused, because Eric Sorensen is with a K, and then I always forget this. Interestingly, with Sorensen, where he was a PhD student, he did very non-Sorensen-like chemistry, this like amino oxygenation, high valent palladium stuff that's quite interesting and important, but not in the typical Sorensen lane. Okay, so I picked this example because it blends concepts from different reaction types that we've covered up until this point. So first, let's take a look at the starting material. As you can imagine, in this paper, there's more than just tetramethyl ethylene. But this one is kind of interesting. So what's going on here? We put in the flask a primary alcohol. We've got cobalt catalyst, DMAP co-catalyst, Bronsted acid co-catalyst, blue LED. A lot going on. So first, let's talk about just the product. What do you think, David?
It's some kind of carbonylation and the alcohol is in.
Okay. So do you like this as the product?
Yeah.
Okay. Does anybody get anything different than this? Anna?
I feel like maybe try and walk into the linear and then eventually you get a linear.
Ah, okay. Why are you uncomfortable with this product?
I feel like beta hydroxylation will be faster than a migratory insertion in this case.
Interesting. Okay, so you favor, if I understand you correctly, this product,
Yes.
and you would be correct. So if you answered this one, the top one, the non-migratory, I think that's not, I mean, you're on the right track, David said. But you do generate in this, if you just think about this mechanistically, you have some kind of hydrometallation most likely, and then you're going to generate a tertiary alkyl metal species. That might not be so happy. It's certainly very sterically encumbered. So if it has the opportunity to undergo beta hydride elimination and chain walk to a less encumbered position, it might do so, which is what Anna was alluding to here. Okay, and then the last part of the question is a catalytic cycle that accounts for involvement of all of this gamish here. Any thoughts on this? Alex?
I think the light is to dissociate CO.
Okay.
Generate coordinatively unsaturated metal center. And I think the acid is probably, you can protonate one of the low valent cobalts to generate a cobalt hydride species. So you do your, you coordinate your olefin, insert the hydride.
Okay, so I'll try to keep up with you. This is good, but I gotta keep up here. Okay, so you say the light is gonna lead to dissociation to this, if I understood correctly. Then you have H plus to get to your hydrido. Is this what you said? And then now you want to protonate this. And then
Yet that's still coordinatively saturated, so I think you can further dissociate one of those COs to generate a free
Okay,
site.
and then,
I would coordinate the olefin and insert.
so we'll just rather, I won't draw out the chain walking process here. I'll just assume that this is a simpler case of an alpha olefin, just for sake of illustration. Hopefully that's okay with everybody. Okay, so we're gonna hydro metallate, and then another equivalent of CO. You have now an acyl cobalt.
So then I think you can either directly displace that with the alcohol or I guess we still need DMAP somewhere in the catalytic cycle, so.
You've got an acyl electrophile. It's not a bad bet to think maybe the DMAP might want to get involved here. And I think they show in this paper that it does work to some extent without DMAP. So if you're asking, do you really need the DMAP or not? And then this kind of say product.
See this will.
Eventually find more. Yeah.
For the initial cobalt different carbon.
Yeah.
Is that not a large one? Do you homolysis on the cobalt to cobalt? Heterolysis.
I think it is drawn as, let me see, I just had the reference up, so that's why I closed my, I think it is drawn as a homolysis.
Then when you prunate that cobalt radical, where does the extra electron come from? Or generate the cobalt hydride? That's charge neutral. Balance. So you from the lines.
Yeah, okay, thank you. So you, yeah, I think they draw it as getting, so you're basically, your point is you need to get one electron here, is that right? And I think they draw this in a slightly different way, actually, where they have this. And it's like this. Oh, sorry.
Let's use same share.
So they draw the nucleophile as involved in the, which I guess is the, either the DMAP or the alcohol is involved in that dissociation step.
Makes sense.
Okay, good. Well, sorry, we're a couple minutes over. We'll wrap things up here. Happy to stay after if there are any questions.